Hi everybody, welcome to MacMind.io. My name is Johnny Mac. I'm a software professional and the host of this channel. Thank you for tuning in today. I'm really excited to share with you about my experience using AI to build and run a Bluetooth low energy server on my Raspberry Pi. Be sure to watch all the way through to the end to learn all the steps to configure your Raspberry Pi to start the service when the device boots or by using some other trigger. But first, why would you want to build a Bluetooth low energy server for your Raspberry Pi? And why use Rust? Did AI do everything for me, or do you need to have Rust experience to do this? So I made a video recently about using rpi-image-gen to build a custom image for your Raspberry Pi. In that video, I explain why custom images for the Raspberry Pi are increasingly important as the hardware is now being used for production applications like digital signage and kiosks. If you're working on a product that includes a Raspberry Pi or a clone of the hardware, you're tasked with providing a gold master device image to ship with your product. And you want to optimize this image for your product use case. If that use case includes having the user connect to the device to set it up, maybe they need to configure the Wi-Fi connection, for example, which is a very common use case, and you or your product owner wants this to be done through an app on a phone, again, very common. Using Bluetooth is a great way to handle this. But why use Rust? If we look at the Rust website, we can see the value proposition is right here. Why Rust? Rust is blazingly fast and memory efficient with no runtime or garbage collector. Scroll down a little bit here, we can see embedded is called out. Need low-level control without giving up high-level conveniences? Rust has you covered. If we write the service in Rust, this allows us to generate a binary that has minimal runtime dependencies. You can compile the binary, copy it into your custom Raspberry Pi image, and it will run on the Raspberry Pi with just the core Bluetooth shared object libraries installed. It will be as lightweight as it gets for such an application, versus a Python option that requires the Python runtime to be installed on the Raspberry Pi. Installing Python on the Pi may seem trivial, but if you're after the highest optimization and most performance solution, Rust is the way to go. I'm sure there are some other ways to achieve this that may not seem as complicated, such as installing the default Raspberry Pi OS and setting up a Bluetooth service via the desktop GUI. To be honest, I haven't attempted any of this, so I don't know how simple or complicated it is. If you've done it that way or another way, let me know in the comments section, and whether you think it's more or less ideal than their solution that I'm proposing here today. Lastly, I used AI for this project, and while it was extremely helpful, I did have to iterate a lot more than I expected. I did have some exposure to Rust, so I wasn't flying completely blind, but I wanted to really challenge AI to do it for me. Using ChatGPT, I was able to get the basic setup fairly quickly. In this case, I was able to run the service and see the device broadcasting using my iPhone to scan. This was pretty cool. You can see it started me out with a Python solution. But then I asked it about Rust, and it was able to help me implement it that way. We went through quite a few iterations, and we even went in a circle at least one time. This is when the AI seems to forget that it provided you a code solution that didn't work. But eventually we got there, and I got pretty excited about this. However, when I went to enhance the functionality, in this case, I wanted to send a timestamp from my phone to the device. It took much longer for AI to get it right. This is around when Grok 3 came online. And so I switched to using Grok 3 to see if it would do better than ChatGPT or Copilot. And you can see it was a lot of iterations before I got it working. We went back and forth here for 1 to 2 hours maybe, working through different errors and issues, versions of the interfaces. It was trying to reference API documentation. In a few cases, I had to actually provide it with the correct documentation, and eventually we did get there. However, it took quite a bit longer than I was really expecting. So we're hearing a lot about how AI will do all the coding, and I'm making a whole nother video on that topic, but my conclusion at this point is you'll need to have some fundamental understanding of Rust and programming to work through the issues, even with AI helping you. So now we understand a little of why we would want to write a Bluetooth low energy service for our Raspberry Pi and how much AI was able to help with this. Why don't we go ahead and hop in and see what this looks like. And so if we're thinking about the structure of this project, we're going to have our Bluetooth service written in Rust. We're going to compile that to a binary, and then we're going to copy that to our Raspberry Pi image. So let's go ahead and start out by creating a directory for our Bluetooth service. And then let's hop in there and create a Docker file for that. And if we're going to use this Docker image to compile a Rust application, let's go ahead and just use the official Rust image as the base. And then we're going to install some dependencies so that we can cross-compile to support the Raspberry Pi chip architecture and the Bluetooth module. And finally, we're just going to set up the working directory for our app. Now let's go ahead and create a Docker Compose file. And this is just a simple single service for now that we're going to use, and we're going to mount the directory we just created into that container so that any files that we generate are going to be persisted to the host. Okay, and we ought to be able to go ahead now and see that we can build this image. Okay, excellent, and we can run it as well. Okay, great. We haven't really done too much yet. We have our base image that has Rust and some dependencies and a Docker Compose file. So now we want to enhance this with our Rust application. So let's do that, and I'm going to go ahead and hop over to VS Code here so that this is a little easier to follow along. And so as you can see here, we have our Docker Compose file and our Docker file. And what we're going to want to do next here is we're going to want to install some dependencies for our Rust application. And this is what I was able to come up with iterating on this with AI. And so we're going to use Cargo to install some dependencies. Cargo is the build, service, and package manager for Rust. And we're going to go ahead and specify some dependencies here. We're going to include Bluer. Bluer are the official BlueZ bindings for Rust. And you may recall we did include BlueZ here as a system dependency in our build service. Later, we're going to also include BlueZ with our Raspberry Pi image. We're also going to install Tokyo, which is an async runtime for Rust, as well as the UUID and futures crates. Then we're going to go ahead and create a simple source code directory, and we're just going to have one source file called main.rs. And again, this is what I was able to iterate on with AI. And I'm not a Rust developer by profession, and I also don't have a lot of experience with Bluetooth interfaces. And so this was a new endeavor for me, but I was able to work with AI to come up with this solution, just prompting it with a simple inquiry: how do I set up a Bluetooth service on my Raspberry Pi? And you may recall it initially proposed a Python solution, but I asked it if we could do it in Rust. And we did have to iterate on it quite a bit. The initial code that it provided did not compile, and we had to go through quite a few iterations to get it to compile. It was using older versions of Bluer, or it wasn't exactly sure how my Raspberry Pi was going to be broadcasting, and so that we could actually connect to it. But this is what we were able to come up with, and not, again, being a Rust developer or having too much experience with Bluetooth, you can get a pretty good sense of what's happening here. And the AI did a really good job at not only providing code, but providing some context around what was happening with this code and why we were writing it this way. And so that was super helpful. And so when we see here, we can take a look, and we're going to create a session, and the session is going to have a Bluetooth adapter. This is the Bluer crate that we're using to create that session. And then we're going to create a characteristic. This is going to be important because a characteristic is the way that your paired device can actually interface with your service. So we'll get back to some of the details of this in a second. Then we're going to define that service and register what's called a GAT application. And then we're going to advertise that this service is available over the Bluetooth radio. And this is how it's set up. Again, we get a pretty good sense of how this is working just by taking a look at this code. And then here we also have some code commented out. This is in case we want to shut down this service after a certain amount of time. That's something that you might want to do if you want to save energy. But we are actually timing out our advertisement. This is going to be important later because you're not going to be able to discover the device when this advertisement times out. Coming back to our characteristic, we have here a simple interface. What we're going to do is we're going to try and set the time on the device from a paired device over this Bluetooth interface. And so this is going to accept a timestamp. We're going to validate this timestamp. And then we're going to use the command struct, which is part of the system process module in Rust, to invoke a command that sets the date and the time. And so this is the code, again, that I was able to come up with iterating on this with AI. So next we ought to be able to open a terminal. And if we go ahead and run this service, we ought to be able to then compile this code. And so let's go ahead and see if we can into this service. And then we're just going to run a command to compile this code, which is the cargo build command, and see if we can compile this code. And so we can see it is compiling our dependencies as well as the dependencies of our dependencies. And then it's going to create a target directory. And since we mounted our local directory into the container, we should see that the binary is available on our host machine. And sure enough, we see here that we have a release with the binary right here. So that's great. So the next thing we're going to want to do is we're going to want to copy this binary over to a Raspberry Pi and see if we can connect to the service that is running when we run this binary on the Raspberry Pi. Okay, so we have our binary, and now what we're going to want to do is copy that over to our Raspberry Pi and run it and see if we can see it working and see that it's broadcasting and that we can connect to it from another device. You may recall I've created a video on how to use rpi-image-gen, and in that video we just created an image where we log in, but we didn't actually copy anything to the device. So we're going to enhance that by creating a project structure for rpi-image-gen where we're actually including files that are going to get copied over in that image. Okay, so let's go ahead and start that process here. So we're going to create a directory called macmind rpi ble server, and then we're going to go ahead and create a Docker file, macmind rpi ble server, and we're just going to use the Docker file from the previous project that we know works. And then we'll make an update to our Docker compose file that's going to configure this service and mount the directory into the running container image so that artifacts that are created in there are available on our local host. Okay, and then we ought to be able to, if we exit out of this shell, we ought to be able to see that we can build these two images now. Okay, and let's see if we can. Okay, great, and that we can also run them. Excellent. Okay, what we're going to do next is we want to create the directory structure that rpi-image is going to understand, and to do that we're going to look at the docs, and if we recall from the documentation, rpi-image-gen expects this directory hierarchy, including this ext-dir, and this is something that we can pass into the build script, and instead of referencing the root of the project, it's going to reference this ext-dir to pick up these subdirectories. And these subdirectories are important. This is what's going to inform rpi-image-gen of how we want our image ultimately structured, including what we want on the root file system, including any binaries that we may want to copy into that image, right? And so what's important here is there's a config directory, a device directory, an image directory, a meta directory, and a profile directory. And so a few things we want to make sure that we are doing. We're going to want to create a directory where we can copy the binary. And so this is going to happen in the image directory. The image directory contains the necessary assets which rpi-image-gen will use to create the output disk image with a particular layout. So we're going to go ahead and put a binary in user local bin, so when it creates the root file system on the Raspberry Pi image, it includes our binary. Furthermore, we need to start thinking about what does that binary need to run. Does it have any system dependencies that need to be installed on the Raspberry Pi? And sure enough, there are a few that we want to make sure we know. We want to install the drivers for the Bluetooth radio on the device. We want to install BlueZ, and we also want to make sure that the general Bluetooth package is installed. And so the way that we do this, if we look here, how do we install custom packages onto the Raspberry Pi? So rpi-image-gen uses this tool called bdevstrap. And I'm not an expert in this utility. What I do know is that there's a YAML file that we can create, and we can specify some packages that we want to install. There's also some other features here that we may be interested in, but for now, the packages is what we want to make sure that we understand, and that's how we're going to set up our directory for the rpi-image-gen to install those packages. Okay, so that's going to happen in this meta directory. The meta directory contains YAML layers, which are individual recipes. Okay, and then lastly, we do need to create a profile so that rpi-image-gen knows that we do have customizations for our ultimate image. So let's just go ahead and create these directories. Now, one thing that I did in the previous project was I used the top level directories and just copied them over from the root of the project, because if you don't have any external directory, rpi-image-gen just uses this to config device image. You can see them here, meta profile. And not knowing exactly what is in those directories that is necessary or isn't, just copying them over is a great way to start. If you were just to create an external directory with these directories copied exactly as they are and pass that external directory into rpi-image-gen's build script, it would build an identical image to the default. And so that's a good way to start getting to know that external directory. Now you have one, and you can start adding and removing stuff from it without actually altering the rpi-image-gen project itself. And that's something that I would encourage, because you don't want to change the state of the rpi-image-gen source code. You can now start to explore and experiment in an external directory of your own. So let's go ahead and start this process of creating our ext dir, and then we're going to create those subdirectories, right? So we have config, and we have our device, followed by our meta, image, then meta, and finally profile. Okay, and so let's go ahead. We'll start with the config. We're going to create a file called macmind pi server config, and this is going to look something like this. We're going to specify the device class and profile, as well as the image layout, boot partition, root partition, the name, and rootfs type. The profile here is important. So the profile that we name here, the value that we provide, is going to reference a file here in the profile subdirectory that needs to have the same name. And this is just going to be a list of layers that we want to inform rpi-image-gen about. And some of these layers are going to be referenced in the top level of the project of the rpi-image-gen application utility. And then we're going to add a custom layer here called customizations. And this is going to live in our meta subdirectory under a file called by the same name, customizations.yaml. So this is essentially how the flow works. You have the config file, you specify a profile. That profile then references a subdirectory called profile with a file of the same name. So I could call this foo and name this profile foo. Then in that profile, you're going to specify which layers you want your image to include. And if you have a custom layer, you can go ahead and add that here, and that's going to be picked up in your meta subdirectory, and that's going to follow this bdebstrap YAML structure. And so for that, we're going to go ahead and use this customization file. And so this is where I can specify some packages that I want to include in my image. So for this, we're going to use dbus. This is the firmware for the radio that's going to allow us to actually use the Bluetooth interface. rfkill, this will come up a little bit later. BlueZ, as you recall, BlueZ is the system level package, and then we utilized Bluer, which are the BlueZ bindings for Rust to interface with BlueZ, and finally Pi Bluetooth. So these are the packages that we need for our Rust application to run and work. And finally, we have some code here. Essentially, the main thing that's important here is that we are adding the Bluetooth privilege, the Bluetooth group, excuse me, to our device user. The rest of this we can ignore for now. If you want to study that, you can do. But for now, the most important thing here is that we're adding the user to the Bluetooth group on the device. Okay, and so if we come over here now, there's a few things that we want to make sure that we also include. Again, if we look at our config file, we did specify the class of this device to be Pi4. So what that means is that rpi-image-gen is going to be looking for a subdirectory in the device folder called by that same name. And this is basically going to ensure that some boot time properties are set when we are building the device image. And that is really going to be the command line text config.text. So those go into the device rootfs overlay boot firmware folder. So let's go ahead and create that device rootfs overlay, and then boot firmware. Okay, and we're going to have a command line text file in here. It's like this, and we're also going to have a config text, and that's going to look something like this. And some of this is just a direct copy from the root project in the rpi-image-gen source code repository with maybe a slight modification. So now we have our device directory. So now our image directory, right? And this is where we're going to want to include our binary. And so when we provide an image directory, we do need to provide all of what is necessary in that image directory in order for the image to be successfully created by rpi-image-gen. It's not, oh, we can't just add one small thing and then have it merge with the image directory from the root. It's going to pull everything from this. And so what I tend to do is copy over from the root project again, and then use that as the starting point and just enhance that. I haven't gotten into optimizing that further. I'm sure that's possible. But for the sake of this project and the simplicity, that's what we're going to do. So I'm going to go ahead and do that, and then you can see where we're going to move our binary. Okay, so I've gone ahead and copied over the image layout from the root of the rpi-image-gen project. And if we come back over to the documentation, the README for the image layouts, we can see that there are two image layouts supported by rpi-image-gen. And one is the Raspberry Pi OS style, and that's in the MBR simple dual subdirectory, and the other is GPT user data and AB capable with a data partition. I don't exactly know what this is or what this means, but I'm going to do another video on this beta feature, so be sure to tune back in for that. For now, we're just going to remove that so that we're not confused. So if we come back over to our project, we can see now that we have a image directory with the MBR simple dual subdirectory, and then this is essentially a straight copy from that root of the rpi-image-gen project. And so how this is going to work is that rpi-image-gen is going to source some configuration from this image layout. And one of the features of rpi-image-gen is that we can use what's called the rootfs overlay if we specify a rootfs overlay folder in our project. And again, if we come back to the documentation, we can see that this feature is called out here at the top level in the README. If we scroll down here, we can find information on the rootfs overlay, and that's going to be what we are looking at here in the overlays section. Okay, and so this is what we're targeting here: image-dir device rootfs overlay. And so that's what we're going to want to create in our project. And whatever we put in that directory is going to be copied into our device image. And that's what we want to do. We want to put our binary there. So let's go ahead and create a device directory here with a rootfs overlay. And then we're going to just put our binary in user local bin. For those of you familiar with Linux, this is a common location to put binary files. It's on the default path, and so this should be a good location for us to put our binary. So we can now go ahead and take a look in our BLE server directory, and in our target release we have our binary, and we can go ahead and copy that, and then we're going to paste it into this user local bin. And so now we have what we need, which is our binary in that bin-dir. Okay, I think the last thing that we do need to do here is we wanted to create an image, so we do need to specify a user, and that's done through our options file. So we're going to go ahead and create MacMind RPI BLE server options, and this is going to just tell rpi-image-gen that we want to specify a device host name, a user and a password, and also give the image a name. This is going to be used to define the file that rpi-image-gen generates, the image file name. Okay, and so with this, we ought to be able to now build an image that has our BLE server in it. And when we install that on our Raspberry Pi, we should be able to run that service. And that's what we're going to try to do next. Okay, so let's go ahead and create a new terminal here, and we'll just go ahead and start our services. We're not really going to use the BLE server container right now, but for simplicity, we don't mind if it's running. And then we'll go ahead and shell into our MacMind RPI BLE server. And then we're going to just see that we have the rpi-image-gen utility, and we also have our customizations that we mounted into that container. If we want to use rpi-image-gen and we want to configure it to know about our custom layout, and how we're going to do that is we're going to pass this directory to rpi-image-gen, the external dir, And then we want to tell it about our configuration as well. This is a little tricky. You don't pass the path to the configuration file. You just pass the name of it. And that tripped me up a little bit a few times, because then when we go to pass our options file, we do need to specify the full path to that. And so this is just a slight inconsistency with the interface, but that's okay. And so when we run this, we ought to be able to see this start to build. And again, if you're familiar with rpi-image-gen, this is a great way to build images for your Raspberry Pi that are customized. I have a whole nother video on that, as I mentioned, and I'll be continuing to use this utility in the videos that I'm making as I prepare more content for Raspberry Pi images. So now we're going ahead and installing, and what it's doing again is it's going to install those customizations that we asked it to install here, which include this firmware, this RFkill utility that's going to come into play in a minute, at BlueZ, and the Pi Bluetooth package that is provided by the Raspberry Pi repository. And again, you can see how fast this is. That's really cool as you want to iterate and try new things. It's just very quick to build these images. And there we have our image that has been generated. So this is now, again, in the container, and we did not copy it to a location that it's going to be available on our host machine. rpi-image-gen is going to deposit the build artifacts into a directory that's in its own namespace, the rpi-image-gen project folder. So we do need to now copy that out of the container that is running. And so we can use Docker copy to do that. Let's create a new terminal here. And if we look at the running containers, we can see that we have RPI BLE, MacMind RPI BLE server here. Let's go ahead and find the path. So this is going to be in our work directory, and we look there, we can see, again, this was configuration that we specified in our image layout. This is what was picked up by rpi-image-gen. The MacMind RPI BLE server is the name. And then we have a deploy directory, and we can see our image RPI BLE server right there. So if we go ahead and use this, we're going to use the absolute path from this container, and we can Docker copy, and we're going to specify the container ID, and then we're going to go ahead and copy this to our MacMind BLE server directory on our local host, and we can see it appear here. Okay, great. And now we have the 3 artifacts that were generated by rpi-image-gen, our image, our sparse file, and our SBOM. Okay, great. So now the next step is to actually install this on our Raspberry Pi and see if we can start the service. Okay, so we're going to go ahead and take our trusty USB drive here. It's a 32 gig SanDisk drive, but if you have anything as big as 4 gigs, you should be fine for this tutorial. And then we're going to use our favorite RPI imager tool, and we're just going to specify the device. I'm not sure the significance of this setting here when we're doing and using a custom image, but just set it to the Pi 4 for our device. And then I go ahead and use custom. This is where you're going to want to locate your image file. If you're on a Mac or Windows or Linux desktop, just locate that image file. And then the storage is just going to be our SanDisk 32 gig. Yes, we want to erase the media without any customizations. Give it our password, and off we go. And now this is writing, and this should be pretty quick because, again, the image that we're generating is very small. One of the benefits of using rpi-image-gen, is that we're creating a cast instead of taking a pre-built image and then customizing that. So the images are going to be very small. And while this is writing out too, one other thing that I want to share is that I did ask AI to help me with this, specifically the Rust BLE server part. And I did also have some challenges in figuring out how to use rpi-image-gen to get the binary to install on the device and also to run, and also then to have it auto start when the device boots, and we'll get to that piece later. And I did also ask AI to help me with this. AI was not super helpful with providing some direction for utilizing rpi-image-gen. It kept thinking that I was using the RPI distro pi-gen tool. Because rpi-image-gen is so new, I think that was really confusing it. And so the help it was providing wasn't useless, was more difficult for me to integrate directly. I had to interpret what it was trying to instruct me to do and then apply that to rpi-image-gen. Okay, so we are back here, and let's go ahead now and see if we can't get this to run on the device itself. And so when I pop this into my Raspberry Pi and boot it up, what I'm expecting to see is I'm going to be asked to log in, and then I should be able to locate the binary that we wanted to put on the device. And we can see that it is asking us to log in. So let's go ahead and log in, MacMind. And then if we go to user local bin, we should see the binary that we wanted on the device. There it is. So let's go ahead and see if we can run that. Again, it's on the path, so we should be able to just invoke it. But we get this error. And so in debugging this error, what we have come to find is that by default, the device has Bluetooth disabled, and that's a security feature. And again, a virtue of using rpi-image-gen to build an image. It's going to be very much in a state that you need to configure everything, okay? And so what we've learned here is that there's a utility called rfkill that has blocked Bluetooth by default. And so that was why we included rfkill when we specified the packages that we wanted to install in our customizations. And so we can use that utility, and we do need to use sudo to go ahead and unblock Bluetooth. Okay. And now when we go ahead and try to run our BLE server, sure enough, we see that we're advertising a set RPI time. And so now what I'm going to do is I'm going to go ahead and use a utility on my iPhone called NRF Connect. And I'm going to go ahead and see if I can't use this to scan for the device that's broadcasting. And sure enough, there it is. And let's see if I can connect to it. And sure enough, I can connect to it. And so that's pretty cool, right? This is pretty satisfying. And what have we done here? We wrote a BLE server using Rust, and we were then able to compile that in a container running on our local machine, copy that compiled binary into the image layout for rpi-image-gen, generate an image that includes that binary, and then when we install that image with one simple configuration to enable Bluetooth on the device, we're able to run that service and now see it broadcast to another device. And so the next step, as promised, is we're going to go ahead and set up the service so that it runs on boot and that we have the configuration preset so that Bluetooth is enabled and the service runs. And then I'm going to go ahead and demonstrate that I can set the time. I've written a little iOS app that allows me to set the time there. So let's go ahead and take that next step. So let's come back here to our code, and what we're going to do now is just go ahead and locate our image layout for rpi-image-gen. And what we're going to do is we're going to add a post build script here. And this is a simple shell script that what we're going to do is we're going to configure some systemd services. And we want to set up the device so that it will unblock Bluetooth, start the service for us at boot time. So to start here, we'll go ahead and enable Bluetooth. We're going to write out a systemd service called unblock Bluetooth. And we can see here, we're just going to run that rf-kill unblock Bluetooth command that we ran on the device. And we're just going to run that when the device boots. Got to make sure to set our permissions and symlink here. We're also going to go ahead and set up the auto login. And you may recall from a previous video, this is the way that we can do that. So we can configure the MacMind user to auto login. And then finally, we want to go ahead and set up the device to start our BLE server when the device boots. So similarly, a systemd service for that. And we're just going to go ahead and configure that as such with specifying the location of our BLE server binary here. Again, setting up the permissions. The last thing that we need to do here is we do need to set a pretty host name, which is in the machine info. And this came up when I was attempting to connect to the device via the iOS app that I built. And even though NRF Connect was scanning and finding the device using the host name that we were broadcasting in our Rust service, when I went to find it using iOS, I was not able to without this additional configuration. So I did iterate on this with AI, and it was helpful in directing me to set up this machine info pretty host name. And so that's what we're doing here. Okay, and the last thing we want to make sure that we do is we want to set the permissions on our build script so that it is executable. And so let's go ahead and locate this here, and then we can set the permissions to ensure that this is executable. And now we can see that it is, okay? And so now I'm gonna go ahead and go through these steps again to build an image, then copy it out of the container, use rpi-imager to write that image out to my USB drive. Then I'm going to take the USB drive, pop it into my Raspberry Pi, and I'm going to demonstrate that the date is set in the past quite a bit. And then I'm going to use that iOS app that I built to set the time. I'm not going to go through the details of that iOS application here. I can create another video for that if there's interest. I did write an iOS app and an Android app to ensure that I was able to set the time using the service that's running on the Pi. So let's go ahead and see if we can make that happen. And so now we're going to go ahead and boot up our Raspberry Pi device and see if we can see this service running and see if we can set the time. Okay, and we can see that the time is indeed in the past. And now if we go ahead and set the time, you should see that the time has been set on our device. Okay. So that's it for this video. Thanks for tuning in today to learn how we used AI to build and run a lightweight Bluetooth low energy server written in Rust on the Raspberry Pi. If you like what you saw, please go ahead and tap that like icon. It would really help me out and give others a chance to see this content. Also, do you have any thoughts or questions? Please share in the comments section. If you have another way of doing this or you want to hear more on this topic, I'd love to hear from you. I hope you're having a great day, and remember, don't stop experimenting, challenging assumptions, and seeking the objective truth. I'm Johnny Mac. This is MacMind.io.